Okay, guys, we're gonna finish up this intermolecular forces here. We got two more. The first is dipole-dipole interactions, and this occurs in polar molecules. You got to remember when we talked about drawing and polar molecules, stuff like that. And what we're looking at here is, fortunately, I got cut off here. Uh, Dipole-dipole interactions with polar molecules. These polar molecules have permanent dipoles, which means there's an area that's positive and negative. Remember, polar bonds are like your fununcle, funkel. We're going to talk about those. They behave like small magnets, and magnets line up with a positive end near the negative end. That's how there's attraction there. So polar molecules, not ionic compounds. Again, I'm trying to hammer this, not ionic compounds. Those are ionic interactions. They must have FON or Cl. Vesper is going to be really important. And so you can see with these polar molecules here, boom, 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 we start to get an increase in boiling point. Now, granted, this is a little bit more all over the map as opposed to when we were just doing molar mass. But if you look at the boiling point of formaldehyde and the boiling points earlier in London dispersion forces, you can see by adding this oxygen, the boiling point goes up pretty significantly. So Boil dipole-dipole interactions do strengthen or raise the boiling point. Uh, this like acts as an add-on to London dispersion forces. It's the dominant force in polar molecules. I'm trying to draw your attention to there. So here, the positives and negatives line up next to each other. That's what we have. And polar interactions allow things to dissolve in water. So if the overall thing is nonpolar, it's not going to dissolve in water. If it is polar, if it has this dipole-dipole interactions, it can dissolve in water. Which brings us to maybe the most important one of them all, and this is hydrogen bonding. All right. Now, H bonding is a special dipole-dipole interaction. Um, Hydrogen bonding is fun. That's it's like the Funkel thing, but it's fun because you need hydrogen directly bound to FO or N. Just because it has FO or N in it doesn't mean it has hydrogen bonding. The H has to be covalently bound to it. Sorry. Because hydrogen only has one electron, you can read this stuff right here. Uh, H is essentially a bare proton. And because it's a bare proton, that one electron is tied up in the bond. All right. So you can see single bond has two electrons. One of those electrons is hydrogen. Those electrons are pulled towards oxygen because oxygen is more electronegative. And what it does is it leaves hydrogen out there, and hydrogen has no electrons on it, so it's a bare proton. Well, protons are attracted to electrons actually really strongly. And what that does is this lone pair on oxygen is really strongly attracted to this bare proton. So what you get is a very strong interaction, and it significantly increases boiling point. So you can see it's strong interaction. Water has a boiling point of 100 degrees Celsius. You got to know that. And then if we just go down, sort of like group six, we have H2O, H2S, H2SE, H2TE. London dispersion forces increase going down, but water has the highest boiling point by a pretty significant margin because of those hydrogen bonds. Ammonia, same thing, much higher boiling point relative to the rest. Now, when we get down here to SbH3, SbH3 is really, really heavy, and so London dispersion forces are going to take over there. All right. So here, there's much NH3 and H2O, they're much higher than they should be. And this increase, like the increase down here, is due to London dispersion forces. You're going to have to identify what sort of intermolecular force is occurring between compounds. So just get ready to do that on the homework assignment.